Uh-huh. Good afternoon, guys. My topic today will be hollow cylindrical method of solution for volume applied to sphere, but the axis of rotation should be horizontally. So this is a topic on hollow cylindrical method rotated along the x-axis applied to a sphere. Okay, let's proceed. This is my lesson number 74. Still integral calculus on my channel under the topic volume, subtopic hollow cylinder method applied to sphere using the horizontal rotation. As always, I always present two solutions, the vertical rotation and the horizontal rotation. So this afternoon, I will show you the horizontal rotation. Okay, I will try to read the problem. Derive the formula for the volume of a sphere using hollow cylindrical method rotated horizontally. If this is the x-axis, the hollow cylinder should be rotated like this. Okay. My previous discussion was that the axis of rotation was rotated vertically. So this afternoon, I will show you the solution using the hollow cylindrical method rotated horizontally. Okay. Let's bring out the figure. Y-axis, x-axis, we draw a circle. As seen from this, you could see a sphere, right? It looks like a circle. On the isometric view, it looks like a ball, okay? I will try to specify the coordinates of this one. This should be R and 0. This one, it should be 0 and R. We don't need this point and this point. We just need these two here, okay? Then by using a horizontal slice, since the rotation is to be rotated horizontally, we use a horizontal slice. Horizontal slice. Okay? We rotate it horizontally. It is this. Okay? I will try to remove this one so you could visualize it. It's like that. That's the horizontal slice. This is XR. This is XL. The thickness is along the vertical, so it should be dy. And the distance of the differential area, that's a small thickness from the axis of rotation. It is measured vertically, so it should be y. And this is the rotation. Okay, let's try to bring out the isometric view. If we try to rotate this one complete revolution with respect to the x-axis, this should be the outcome. It's a hollow cylinder. That's why the topic is hollow cylinder method. There's a hollow at the middle. It is not yet solid. Okay, so this is the center of the axis of rotation. And the radius of that horizontal strip with respect to the axis of rotation is y. This is the radius, it is y. The thickness is dy, and this length here is actually xr minus xl. It is this, the difference of xr minus xl. Xr is actually the abscissa on the right, xl is actually the abscissa on the left, considering the horizontal strip. Because as the horizontal strip moves from 0 to R, okay, that horizontal strip length is actually varying. So I place it, the variable length is actually XR minus XL at any moment. Okay, let's try to cut this hollow cylinder and we try to spread out. What will come out is this. This total length now will be the circumference. Circumference now will be 2 pi y because the radius from the center of rotation is y, So this should be 2 pi y. The thickness is dy, and this length here is actually the variable length of the differential area. It is xr minus xl. Okay, let's try to bring out the solution for a hollow cylinder method. For a hollow cylinder method, to compute for the differential volume, just take this area here times the thickness. So it should be xr minus xl times the circumference times thickness. Or in short, it will be circumference times thickness times height. Substituting values now, differential volume will be 2 pi y times dy times the quantity xr minus xl. So as you could notice it, the differential volume now is expressed as a function of xr minus xl times dy. Okay? There's a problem here. Why? These are abscissas, and the differential thing on the right is dy. So to compute for the volume, compute for xr as a function of y, because this was dy, and we compute for the value of xl also as a g of y. Okay? We must have to derive xr as a function of y and xl as a function of y to integrate. To compute for xr, xr is actually the variable abscissa of the circle, okay? This portion here, it's varying. So it is actually a circle with center at 0, 0. The equation is actually x squared plus y squared equal to r squared. Solving for x squared will be r squared minus y squared. Taking the square root of both sides, okay? These two here cancel with this. What will remain on the left will be xr. I will remove the subscript first. It will be x. And the value on the right will be r squared minus y squared raised to the 1/2 of that is square root of r squared minus y squared. I will now try to place the proper subscript. The computed value of x here is actually xr. It is this. Because this is xr is actually moving like this. Okay, it follows the path of the circle. So actually what we are computing from this is actually the variable abscissa of the circle. So actually xr refers to the variable abscissa of the circle. Xr now will be the square root of r squared minus y squared, equation number 2. It is actually circle, as you can see. This was the center 0, 0. Okay, the radius is r, and the equation is this. That's why we use this. And xl, what is xl? As you could notice it, as this differential area moves upward, the movement is actually a straight line. So actually, we are computing for the value of xl, and we know it from the graph. It is a straight vertical line, and the value is actually xl equal to 0. Why 0? The value of abscissa on the y-axis is actually 0. So the equation of xl, in terms of a complicated or not so complicated, but for the meantime, this is not complicated because xl is just 0. Okay? Equation number 3. A vertical straight line, BSL. So actually, we are now given xr as a function of y, xl as a g of y. Substituting 2 and 3 back to equation number 1, we will go back here. Therefore, differential volume will be 2 pi, okay, times xr is actually the square root of r squared minus y squared minus 0, close bracket, y dy. If we try to multiply this one, this here got no effect. We multiply. Differential volume now will be 2 pi y, the square root of r squared minus y squared dy. So actually, we are now given differential volume as a function of y dy. Okay? And actually, we could now integrate. Right? The variable here is y, so the function should be in terms of y. That's why we derive equation number 2 and 3. Integrating, as you could notice it seems the integration is under the power formula. it is under the integral of u to the n du. And they should be u raised to n plus 1 over n plus 1. But we must have to verify the value of u. The value of u is the one inside. U is actually r square minus y square. Du will be, r square is constant, the differential is 0, so this should be 0. Minus y square, it falls under the power formula. This is minus 2y dy. Or du now will be minus 2y dy. It is not exact. It is almost the same as this, except for the negative sign. Negative 2. It's missing the negative 2. Okay, if we try to insert negative 2 inside, then we place a negative 1/2 outside. This is negative 1/2, right? Negative 1/2. Okay, we insert this negative 2, but we must have to counter that one by placing negative 1/2 outside the integral. Therefore, the integral of differential volume over 2 equal to negative 1/2, the integral from 0 to r. I am following this. 2 pi, the square root of r square minus y square times minus 2y dy. And the integration of this falls under the power formula. So this should now be minus 2 pi. Actually, this 2 here cancel with this. Why there is an over 2? Because from the figure, we are only rotating the horizontal slice one half of the area. So to compute for the total volume, we will multiply it by 2. That's why this was differential volume over 2. Okay. We rotate 1/2, so to compute the total volume of the sphere, make it times 2. So therefore, volume now will be equal to minus 2 pi. It's negative. R square minus y square, 1/2 plus 1 is 3/2, all over 3/2, with the limit from 0 to r. Volume now will be, this 2 here goes up, so this is minus 4 over 3 pi. If we try to place the upper limit, r square minus r square will be 0, 0 to the 3/2 will be 0, and 0 over, it's still 0. So if we try to place the upper limit, the value of the function is 0, minus the value of the lower limit. But when y is 0, this will just go only r square minus 0, or simply r square raised to the 3/2. These 2 here cancel with this. This is negative, negative. This will now be plus 4/3 pi r cube. So this is r cube. It is understood to be plus if there is no negative sign. So the final formula for taking the volume of a sphere using the horizontal rotation is volume is equal to 4/3 pi r cube. It is the same as the last solution the last time around using the vertical rotation. So the significance of the solution here is that whether you use vertical rotation or horizontal rotation, the derived volume should always be the same. Okay, good afternoon, Los Angeles.